We're so used to finding shocking discoveries in outer space that we may overlook some of the wonders happening right underneath our feet. One such amazing discovery is this huge structure buried deep inside the Earth that's been going off like crazy recently. What is the strange object, and does it pose a danger to us? In this video, we join scientists as they detect a massive structure inside the Earth that keeps sending us thousands of messages. The Earth is full of phenomena that you can set the time by. One of the most popular examples is the Old Faithful geyser in Yellowstone National Park in Wyoming. This natural wonder predictably sprouts water every 44 minutes to 2 hours. There is another regular rhythm known as circadian rhythms, which is the physical, mental, and behavioral changes that follow a 24-hour cycle in response to light and darkness. Circadian rhythms affect most living organisms, including humans, animals, plants, and microbes. Circadian rhythms regulate sleep-wake cycles, hormone secretion, body temperature, and other biological functions. However, few are as crazy as the vibration recently detected to be coming from deep within the Earth at a constant rate. In fact, scientists confirm the vibration goes off every 27 seconds. The problem is that scientists are still grappling to find the origin of this mysterious vibration. The Earth tremors every 27 seconds, and it's strong enough that seismologists on many continents detect a significant blip on their detectors. Despite the fact that this pulse has been seen for decades, scientists cannot agree on what is producing it. The uncertainty, however, does not prevent the phenomenon's enigma from even having its own XKCD web cartoon. The pulse, or microseism in geologist jargon, was discovered in the early 1960s by a researcher named Jack Oliver at the Lamont Doherty Geological Observatory. He is well recognized for his later work, which provided vital early evidence for shifting tectonic plates. Oliver deduced that the pulse originated somewhere in the southern or equatorial Atlantic Ocean and was strongest during the summer months or winter months in the northern hemisphere. Jack obviously didn't have the resources in 1962 that were available in, say, 2005. He didn't have digital seismometers, and he was dealing with boring paper records. Gary Holcomb, a geologist at the United States Geological Survey, investigated the strange microseism in 1980 and discovered that it's strongest during storms. But his and Oliver's efforts would be mostly lost to time, while the relentless seismic drumbeat beneath our feet would go unnoticed. Then, in 2005, Greg Benson, a PhD student at the University of Colorado Boulder, began working with seismic data in his lab. When his advisor entered, he asked him to show him what he was working on. According to Ritzvoller, Benson looked up some data, and there it was, a strong signal from a long distance away. As soon as he saw this, Benson and his colleague knew there was something strange going on, but they had no idea what it was. Perplexed, the team investigated the blips from every aspect available. Was there a problem with their instruments, or perhaps their analyses? Or was there truly earthquake activity? Everything pointed to the latter. They were even able to pinpoint the pulse's origin, a single source in the Gulf of Guinea off Africa's western coast. They also dredged up Oliver's and Holcomb's work and published a report in Geophysical Research Letters in 2006. However, no one has really proven the reason for the recurrent seismic activity since then. Many people believe it's created by waves, but some believe it's caused by volcanic activity. Though this particular pulse is noteworthy, the notion that seismic activity occurs during a tranquil period, that is, not during an earthquake or volcanic eruption, is old news. There is always a backdrop of minor seismic noise around us. Examples of regular vibration include the Earth's hum, the continual low-frequency vibrations of the Earth, which can be observed by seismometers in the absence of earthquakes. And scientists have long known that earthquakes can cause the Earth to ring like a bell for days or months. But the discovery of this background noise, which remains even when the globe is seismically quiet, perplexed them. The first trustworthy reports of Earth's hum came from the United Kingdom in the mid-1970s, when Bristol residents complained about a mystery rumble that affected their sleep and well-being. The deafening loudness was even blamed for 2 suicides, according to others. Similar reports have since been received from numerous areas throughout the world, including Hythe, Plymouth, Swansea, New Zealand, Japan, and the US. Many theories and investigations have been conducted throughout the years to determine the origin and nature of Earth's hum. atmospheric disturbances, jet streams, ocean waves, volcanoes, human activities, and even extraterrestrial communications have all been posited as possible causes. None of these ideas, however, can account for the complete spectrum and characteristics of the hum. The most widely accepted idea nowadays is that the hum of the Earth is caused primarily by ocean waves interacting with the solid Earth. When ocean waves meet or travel across a sloping ocean bottom near the coast, they can generate pressure pulses on the sea floor. These pressure pulses can then cause seismic waves to travel through the Earth's crust and mantle, causing global shaking. According to this theory, the Earth's hum is primarily composed of surface waves with frequencies ranging from 2 to 20 millihertz, which are too low for humans to detect. The hum is stronger in the Pacific Ocean, where storms are more common and violent, and it varies seasonally and geographically based on marine conditions. Large earthquakes can also regulate the hum, briefly increasing or decreasing its amplitude. Now, the Earth's hum may appear to be a little curiosity, yet it has enormous ramifications for seismology and geophysics. Scientists can learn more about the structure and dynamics of the Earth's interior as well as its interactions with the atmosphere and ocean by analyzing the hum signal. The hum can also tell you about the worldwide temperature and weather patterns, as well as natural disasters like tsunamis and volcano eruptions. Another type of vibration from within the Earth is the previously mentioned microseisms. These are little Earth tremors induced by natural or human-made causes. They are the most common sources of background seismic noise on Earth, and they are largely made up of Rayleigh waves that travel through the Earth's crust and mantle. Seismometers can detect microseisms wherever on Earth, and they can provide important information about the structure and dynamics of the Earth's interior, as well as the Earth's interaction with the atmosphere and ocean. The interaction of ocean waves with the solid Earth is the primary cause of microseisms. When ocean waves meet or travel across a sloping ocean bottom near the coast, they can generate pressure pulses on the sea floor. These pressure pulses can then cause seismic waves to propagate through the Earth, resulting in a worldwide tremor. The frequency and characteristics of microseisms vary depending on the type and source of ocean waves that generate them. Microseisms are categorized into two types, primary and secondary. Surface gravity waves in shallow water cause primary microseisms. These microseisms have the same time as the water waves that cause them, which is approximately 16 seconds. Primary microseisms are less powerful than secondary microseisms and are mostly identified by vertical seismometers. Now, surface gravity waves with nearly equal frequency but almost opposite orientations interact to produce secondary microseisms. The period of these microseisms is half that of the water wave period, which is normally between 4 and 10 seconds. Secondary microseisms are more powerful than primary microseisms and are identified mostly by horizontal seismometers. The Earth's hum, which is a modest but noticeable excitation of the Earth's free oscillations or normal modes, is another type of microseism. The Earth's hum has frequencies ranging from 30 to 1000 seconds and is most likely caused by the interaction of infragravity waves with ocean bottom topography. Vertical seismometers can detect the Earth's hum, which can give information on the structure and dynamics of the Earth's core and mantle. Microseisms are a source of knowledge as well as noise for seismologists. Scientists may learn more about the features and changes of ocean waves by analyzing the microseism signal, which can be used to investigate global climate and weather trends, as well as natural disasters such as tsunamis and volcanic eruptions. Using techniques such as ambient noise tomography and interferometry, microseisms can also be utilized to examine the structure and dynamics of the Earth's interior. Seismic noise basically exists because of the sun. The sun heats the Earth more near the equator than at the poles, causing winds, storms, ocean currents, and waves. When a wave strikes a cliff, its energy is transferred to the land. It sounds a bit like you tapping on your desk. It deforms the area near your knuckle, but is then transmitted across the entire table. So someone sitting on the other side of the table, if they put their hand or maybe their cheek on the table, they can feel the vibration. Now, the sun provides light and heat for life on Earth, but it also has more subtle effects on our world. One of these methods is to cause Earth tremors, which can be observed by seismometers and other devices. These vibrations are created by solar phenomena such as the sun's spin, magnetic fields, sound waves, and solar flares. The rotation of the Sun is one of the primary causes of vibration on Earth. The Sun revolves faster at its equator than at its poles, resulting in a differential rotation that produces a strong magnetic field. The spinning of the Sun twists and stretches this magnetic field, resulting in complex patterns of magnetic loops and arcs on the Sun's surface. These magnetic structures have the ability to store massive quantities of energy, which can be released abruptly in the form of solar flares and coronal mass ejections (CMEs). Solar flares are strong bursts of radiation caused by the Sun's magnetic fields reconnecting and exploding. CMEs are massive clouds of plasma and magnetic fields blasted into space by the Sun. Solar flares and CMEs can both have an impact on the planet by interacting with its magnetic field and atmosphere, causing geomagnetic storms that can impair communication systems, power grids, and satellites. And solar flares and CMEs can potentially induce Earth vibrations by generating seismic waves. These waves are comparable to earthquakes, but they originate from the Sun rather than the Earth's interior. Helioseismic waves, also known as sunquakes, can be observed by seismometers on Earth's surface or by spacecraft orbiting the Sun. Sunquakes are created by the abrupt release of energy from solar flares and CMEs, which generate shock waves that travel through the Sun's interior and surface. These shock waves can then trigger acoustic waves, which travel across the interplanetary medium and eventually reach the Earth. Acoustic waves can then pair with seismic waves in the Earth's crust and mantle, causing vibrations that seismometers can monitor. And the sound produced by the Sun is another source of vibration on Earth. The Sun is a loud star that constantly releases sound waves owing to convection bubbles hitting its surface. These sound waves have extremely low frequencies that humans cannot hear, but they can be detected by specialized instruments such as helioseismometers. The study of sound waves inside the Sun, which can provide information about its structure and motion, is known as helioseismology. Scientists can deduce temperature, density, pressure, and rotation rate by analyzing how these sound waves travel through different layers of the Sun. Scientists can also use helioseismology to better understand how the Sun generates its magnetic field and how it influences its activity cycle. The Sun's sound waves can also affect our planet by causing vibrations on its surface. These vibrations are created by sound wave resonances in the Sun and the Earth's atmosphere. The Sun's sound waves have frequencies that match some of the natural oscillation frequencies of the Earth's atmosphere, which are known as Schumann resonances. Schumann resonances are electromagnetic waves caught between the Earth's surface and the ionosphere, an upper atmospheric layer of electrically charged particles. These waves are impacted by sound waves from the Sun, as well as lightning strikes and other natural events. When these sound waves reach the Earth's atmosphere, they can resonate with Schumann resonances, causing tremors that seismometers can detect. And gravity, rather than electromagnetic or acoustics, is a third cause of vibration on Earth. The Sun's gravitational influence extends to all objects in the solar system, including the Earth. This pull causes a small deformation of the Earth's shape, resulting in tides in both the oceans and on solid ground. The Sun's and Moon's tidal forces induce periodic variations in both horizontal and vertical displacement of places on the Earth's surface. Geodetic equipment such as GPS receivers or tilt meters can measure these displacements, and they can also cause changes in rock stress, which can lead to earthquakes or volcanic eruptions. So how do scientists measure these vibrations? Well, they use a device previously mentioned known as a seismograph. A seismograph is a device that records seismic waves induced by earthquakes or other sources of Earth vibration. Seismic waves are ground movements caused by the release of energy in the Earth's crust or mantle. Seismographs can determine the amplitude, frequency, duration, and direction of these waves, as well as the location, magnitude, and type of seismic event. Seismographs operate on a rather simple principle. A simple seismograph is made out of a solid base and a heavy weight suspended from a spring over the base. A pen hangs from the weight, while a rotating drum filled with paper lies on the base below it. The tip of the pen makes contact with the drum. The base moves with the ground, but the weight and pen remain stationary due to inertia. As the drum rotates, the pen traces a wavy line on the paper. The form and size of the line represents the seismic wave properties. The horizontal axis of the line represents time, and the vertical axis represents ground displacement or velocity. Now, a seismograph can only detect one type of ground motion, such as vertical or horizontal motion. As a result, the majority of seismograph stations feature 3 seismographs oriented in different directions: north-south, east-west, and vertical. Scientists can calculate the 3-dimensional motion of the ground at that place by combining data from these 3 seismographs. These days, to detect ground tremors, modern seismographs employ electromagnetic sensors rather than mechanical pendulums. These sensors are made up of a wire coil and a magnet that generate electric signals when they move in relation to each other. Analog or digital circuits then amplify and record the electric impulses. A seismogram is a recording made by a seismograph. A seismogram depicts many types of seismic waves that arrive at various times and have varying amplitudes and frequencies. P waves, which are compressional waves that travel quickly through solids and liquids, are frequently the first to arrive. S waves are shear waves that travel at a slower rate than P waves and exclusively through solids. The last waves are surface waves, which are waves that travel along the Earth's surface and produce the majority of damage. Scientists can determine the epicenter and focus of an earthquake by analyzing seismograms from various sites, which are the points on the Earth's surface and inside the Earth where the earthquake begins. They can also assess an earthquake's size and intensity, which are measures of how much energy is produced and how much damage an earthquake causes. Now, seismographs have several uses besides detecting earthquakes. They can also be used to monitor volcanic activity, search for oil and gas deposits, investigate the structure and dynamics of the Earth's interior, and test nuclear weapons. One of the largest repository of data on the Earth's movement is the United States Geological Survey, USGS. The USGS is a federal institution that monitors and researches natural disasters such as earthquakes. One of its primary responsibilities is to maintain real-time data vibrations within the Earth caused by seismic waves generated by earthquakes or other sources. These records are critical for finding and characterizing earthquakes, estimating their effects and hazards, and giving timely information to the general public and emergency services. The USGS operates a network of seismographs which, as mentioned, are equipment that detects and records seismic waves to keep real-time recordings of vibrations within the ground. Seismographs are made up of sensors that monitor ground motion in various directions, as well as recorders that store or send the data to a central point. To prevent noise and interference from external sources, the sensors are normally buried below or mounted to a concrete pier. The USGS uses many types of seismographs for various purposes. Some seismographs are designed to detect powerful vibrations caused by huge earthquakes, while others are sensitive enough to detect weak motions caused by tiny earthquakes or even ambient noise. Some seismographs are broadband, which means they can record a broad range of frequencies, but others are narrowband, which means they can only record specific frequencies of interest. Some seismographs are analog, producing a continuous trace on paper or film, while others are digital, converting the signal into binary code that can be stored or transferred electronically. The USGS operates over 2,000 seismograph stations around the United States and its territories, as well as some in other nations. These stations are part of the Advanced National Seismic System (ANSS), a federal, state, regional, and university partnership to increase earthquake monitoring and research. The ANSS's goal is to offer high-quality, uniform data from seismographs, as well as timely and dependable information products such as earthquake locations, magnitudes, shaking maps, and alerts. Seismograph data is transferred in real time to regional seismic networks, which process and analyze the data with specialized software and technology. The data and information products are then sent to the USGS National Earthquake Information Center (NEIC), which serves as the central center for earthquake monitoring and reporting in the United States. In addition, the NEIC gets data from international seismic networks and collaborates with other authorities and organizations worldwide. The NEIC maintains a comprehensive collection of earthquake data and information products which are available to the public via a variety of platforms, including websites, mobile apps, social media, and email notifications. In addition, the NEIC publishes research reports and publications on earthquake activity and dangers. The NEIC attempts to offer accurate and fast earthquake information to aid in decision-making, risk reduction, and public safety. Researchers can investigate patterns in ambient seismic noise to learn about the Earth's innards, as Ritzwoller's group has done for decades, but the observation of the pulse traced to Bight of Bonny caught them by surprise. Fast forward some years and another graduate student, Garrett Euler, arrived this time in the lab of seismologist Doug Wiens at Washington University in St. Louis. Euler limited the source of the pulse even more to the Bight of Bonny in the Gulf of Guinea. He also argued that waves hitting the coast were most likely the cause. Wiens argues that when waves travel across the ocean, the pressure difference in the water may not have much of an effect on the ocean floor. But when it hits the continental shelf, however, the pressure deforms the ocean floor, much like hammering on a desk, deforms the surface and creates seismic pulses that reflect the wave motion. And in 2013, Euler presented his findings at the Seismological Society of America's annual meeting. However, not everyone was completely convinced. In the same year, a team led by Yingji Xia of the Institute of Geodesy and Geophysics in Wuhan, China, claimed the 26-second pulse was most likely caused by volcanoes rather than waves. The origin of the pulse is uncomfortably close to a volcano on the island of Sao Tome in the Bight of Bonny. And certainly there is at least one other location on Earth where a volcano causes microseism identical to this one. If you're wondering, it's Japan's Aso volcano. Aso volcano, located on the island of Kyushu, is one of Japan's largest and most active volcanoes. It is composed of a caldera and many craters and cones, some of which have erupted often in the past. On October 20th, 2021, Aso volcano erupted, spewing ash and gas into the sky and reaching a height of 3.5 kilometers or 2.2 miles. Aso volcano generates seismic waves that travel through the Earth's crust and mantle, causing earthquakes across Japan. Seismic waves are elastic energy that transfer energy away from the source of an earthquake or volcanic eruption. Seismic waves are classified into two types: body waves and surface waves. Body waves flow through the Earth's interior and are classified as primary P waves or secondary S waves. P waves are faster-moving, compressional waves than S waves, which are shear waves that generate sideways motion. Surface waves travel along the Earth's surface and are classified as Rayleigh waves or love waves. Vertical motion is caused by Rayleigh waves, while horizontal motion is caused by love waves. The magnitude and the frequency of the Aso volcano's vibrations are affected by various elements, including the magnitude and depth of the eruption, the distance from the volcano, the direction of wave propagation, and the qualities of the Earth's layers. In general, the greater and more frequent the vibrations are, the closer you are to the volcano. The intensity of the vibrations is also affected by the direction of wave propagation, since some places may suffer constructive or destructive interference from seismic waves. The density, elasticity, and viscosity of the Earth's strata also influence how seismic waves are reflected, refracted, or attenuated as they pass through different media. Aso volcanoes' vibrations can cause buildings and structures to shake, landslides and avalanches to occur, infrastructure and utilities to be damaged, transportation and communication systems to be disrupted, human health and safety to be impacted, and natural ecosystems to be altered. The negative effects of volcanic vibrations can be reduced by installing seismic monitoring and early warning systems, enforcing building codes and standards, preparing emergency plans and supplies, educating and informing the public about volcanic hazards and risks, and improving cooperation and coordination among various stakeholders. However, in regard to the Bight of Bonny, more questions remain even outside of the primary argument. Specifically, why here? There are dozens of other continental shelves and volcanoes across the world that aren't creating seismic pulses, so what makes the Bight of Bonny so unique? However, nearly 60 years after the pulse was first recorded, no one has of yet figured it out.